السلام عليكم.
عليكم السلام ورحمة الله.
عليكم
كويس يا
السلام.
شباب. أنا بستخدم الكلمة يا شباب للشباب والناس اللي ممكن يكون عندهم أولاد وبنات في ماليزيا وفي حتات تانية يعني. كويس. آه، أنا المتحدث كده بكون ظهر في الصورة. أنا اسمي محمد جاد كريم، وأنا جزء من يوكانا. الليلة احنا سعيدين حيكون معانا الدكتور مجدي أبو القاسم محمد، وهو اي تريبل اي ممبر. ودكتور مجدي أبو القاسم تحصل على بكالوريوس الشرف من كلية الهندسة Electrical Engineering، وطبعا نقصد جامعة الخرطوم طبعا. وتحصل على درجة الماجستير في الكمبيوتر ساينس، ودرجة الدكتوراه في الإلكتريكال أند كمبيوتر انجينيرينج. الدرجتين الأخيرات الماسترز والبي اتش دي من يونيفرسيتي اوف ميزوري كولومبيا. أنا حفظت التواريخ، لكن البي اتش دي in 1995. من العام 1985 للعام 1988 عمل دكتور مجدي as a teaching assistant at the Computer Center University of Khartoum. ودي الفترة اللي أنا محمد جادة تعرفت فيها على الدكتور مجدي أبو القاسم في مركز الكمبيوتر جامعة خرطوم يعني. وكذلك عمل في السودان كمهندس كهربائي واتصالات في سودان ناشونال برودكاستنج كوربوريشن إن أم درمان في الفترة من 91 التواريخ والسكيبت. في الفترة من 91 ل 95 he was a research and teaching assistant in the Department of Electrical and Computer Engineering, University of Missouri, Columbia, طبعا United States. He worked as a visiting professor in the computer engineering and computer science في Department of Missouri, Columbia من العام 95 للعام 96. عنده تجربة طويلة مع موتورولا في 1900، واشتغل في اللابس بتاعت موتورولا Physical and Digital Realization Research Center of Excellence. وكذلك السنتر ده في إلينوي. He was inducted into Motorola Science Advisory Board Association بين قوسين SABA في العام 2007. دكتور محمد اللي هو مجدي worked as a technical director للمجموعة شركة اسمها NIITEK. بعد ذاك لقدام ممكن تفصل يعني الابريفيشنز دي يعني. as a principal engineer also as a principal engineer at Qualcomm Inc. والانترست حقته تشتغل في المالتي ميديا ريسيرش اند ديفلوبمنت اند ستاندردز كمبيوتر فيجن سيستمز. والتجربه العمليه كانت في كاليفورنيا مدينه سان دييغو. في الفتره الاخيره دكتور محمد established an initiative called Advanced Metrics for improving computer vision, pattern recognition, and machine learning techniques. الانيشيتيف دي في San Diego, California. His research interests include multimedia, automatic target recognition, landmine detection, real-time change detection, pipe inspection, offline and online handwriting recognition, optical motion tracking, digital signal image and video processing, computer vision, fuzzy sets and systems, and neural networks, pattern recognition, parallel and distributed computing, nonlinear and adaptive modeling techniques, machine intelligence, fractal and chaos structures, energy aware processing, and contents aware computing. وتحصل على إجازات واحتراف for outstanding research contribution with several institutions and awards, including 2003 IEEE Transaction on Fuzzy Systems, Outstanding Paper Award for the papers العنوان المنشور كان Generalized Hidden Markov Models Part 1 and 2 presented by IEEE Neural Network Society في العام 2003. هو شغال الدكتور مجدي في الشركات وفي المجالات بتاعت الريسيرش اند ديفلوبمنت، وفي جزء منها جزء فيه بيتنت، وفي جزء منها فيه اوثرايزيشن هو بيتكلم عنها يعني. فتفضل يا دكتور مجدي، وانا بيوميوت، وارجو لو في اي جزئيه ما تكلمت عنها في التعريف مرحب بك يعني. شكرا جزيلا.
ما قصرت حبابكم يا هنا. الحقيقة عندي سلايدز كثيرة حتغطي معظم الأشياء ذكرها جاد كريم. I picked the title Computational Intelligence and Statistical Learning Programs. In this regard, by computational intelligence, we mean three main things: neural networks, genetic computing, and fuzzy logic. So I'm going to touch on those and describe to you how machine intelligence is really important for a lot of use cases. So I'm going to go over some of the use cases as well. So at first, I'm going to provide some history about my experience and how I spend my time developing those techniques. If you have questions, feel free to ask. I'll try to go fast on some of the pages just for connections, and I'm going to stress on the new material that you might not be able to see in textbooks or so. But when I was in Motorola, actually, we had a project called telepresence communications. And what you see in front of you is how we can translate video. Human language translator. And the idea is if I'm talking in front of my phone in one language, you can see my face in your at your end. You're speaking in a different language, and you see my face with the translated language.
يعني إذنك يا دكتور مجدي ممكن تكبر الشاشة أكثر على إنه يعني تعملها فول سكرين.
الشاشة دي صغيرة. I'm trying. If I try to do the slide show, probably we are going to lose it.
Okay. في الحالة دي واصلة.
Okay. How can you see the slide show now?
لا ما ظاهر.
It's. Can you see the slide show now?
Yeah, that's better. Yes. كده أحسن.
Okay,
Yes,
this
كده
is the
أحسن.
slide.
Thank you. Yes.
Okay,
Thanks. Continue.
so the system that I'm describing here is using machine intelligence in every box. ASR, automatic speech recognition, facial expression analysis from the video. We convert the text we get from ASR, and we use translating a text. Then text to speech, TTS, will generate phonemes, and those can animate a 3D model of the face. As I mentioned before, every box here is using machine intelligence program, and we want to do it real time. That's a bigger constraint, actually. While I was talking, you see me talking in your language, and I don't know what language you are listening to. Okay, so this is just one thing to drive the discussion that I'm going to go over. So if you see in slide 2, adaptive solutions, can you see that? Hello?
نعم yes. تواصل.
I am seeing slide 2 in front of me right now. Can you see it yet?
Yes, adaptive solutions. Yeah, yes, that's
Yes,
frontier.
yes.
Yes,
So
okay.
that means
Yes.
the presentation mode is working, because last time it wasn't working for me. So the name of the game here is we need techniques that can adapt with the data. And linear models, even for the neural network, when you start with a linear perceptron, it was not solving problems like the XOR problems. So everything we do is actually using using the linear techniques to do so. So if you see the motivation, application, tracking, image processing, pattern recognition in general, and there is a lot of theories behind what's running. And you see a lot of filters based on probability measure. Kahneman filter, hidden Markov model, condensation filters. I'm just putting some dates to give you a feel about how when that started actually. And there is robust estimation. Those like nonlinear filters, like morphological filters and stack filters, I'm building on those. And for better recognition, even neural network start with the feed forward. Shared weight network is what's being called now convolution neural networks. And the main thing is back propagation. I'm going to go over that in the slide. I'm just trying to put the topics in one slide so that I can connect the pieces. And I'm going to talk a little bit about support vector machine, which is like a neural network, a statistical neural network, if you like, where the weights are probabilities. Well, from object tracking, we can go to automatic control, from image processing to computer vision, which is analyzing the image. And in general, neural networks are used for a lot of things in financial predictions, data things. So the techniques I'm going to describe to you, and that's the core of this first session, is actually using non-additive measures, which include probability measure, which is additive as a special case, and nonlinear integrals. I'm going to talk a little bit about that to justify why those are powerful, and they are allowing me to do the number crunching more fast, and I get more accurate results, if you like. So in today's presentation, I'm going to introduce to you something that's probably you haven't heard about before, called Q filters. and few machines. And I'm going to talk about logic because reasoning is a very essential part of any computational intelligence techniques. So the the use of filters is for feature extraction, which is computing numbers that characterize the input for the sake of analysis. And the machines are those classification or regression or density estimation techniques. We call them machines. And I'm going to talk about logic uh, at the end of today's presentation. Before talking, maybe next presentation, we are going to talk about large language models and those kind of things. So what you see here is where that skew filter stays. It's actually trying to represent or characterize all or most of the classical filters in just one mathematical formula, which is very challenging actually to be able to do that, because now if we build just one hardware for this filter, we can accelerate all the classical filters, and we just programming it is just a single number that's changed the behavior from dilation to erosion, for example, and so on. This is just what's happening, if you see my cursor, in a node. And of course, we construct a network of those nodes to be able to solve the problems at hand. So this is motivated by image processing and signal analysis in general. So if you look at the tracker bar, we have, for example, here, an image is characterized by pixels from pixel 1 to pixel n. We do some normalization, size, light, pose for the head, for example. And we do a lot of pre-processing. We change it to binary, we remove noise, we smooth it, and we do segmentation. So I wanted to know where the eye is, where the mouse is, and we use a lot of morphological operations to do so. Feature extraction, we can do edge detection, thinning, linking, and so forth. Then the analysis part is the most difficult part. That's where the machine learning is heavily used. And we do post-processing, then we convert the input to action units, A1 up to AC. Those are what's going to be used in the decoder to generate what we want it to do with the input image. Interestingly, all of those operations are filters. So that's why this notion about having a universal filter can help us in all the pipeline. People have designed hardware just to do dilation, for example. That's a morphological filter, or erosion, or whatever. The problem is for each specific filter and with the window size, with each specific window size, we have to use a dedicated hardware. Of course, if the problem is big, that's going to be expensive to have different hardwares. And even if I change the window size, so you need to change the hardware. That's not a good idea. So the reason for this filter, which we design with machine intelligence to generate its parameters, is actually helping us to get around this bottleneck of the hardware. And I called it Q filter. This is my contribution actually to Motorola Labs when I was over there. working on this project, I have to develop theory to justify that we should build just one hardware and it's supposed to do all the pipeline processing, if you like. So there is some literature that's being published. The letter Q here is for quotient, actually, because we defined something that they called Q measure, which includes the probability measure as a special case. It turns out to be a quotient of polynomials. So Q for quotient, and it's very quick because we wanted to solve real-time problems. So the IEEE paper that Jad mentions in the introduction is actually what triggered this Q filter story, because it's designed, it tried to generalize the statistical, the probabilistic hidden Markov model to do more than probability measures. And the trick is actually how to combine pieces of information with a proper measure. And the tool that we use is introduced by a scientist called Choquet, a French scientist, long time ago. It's the core of what's called theory of capacities. I'm going to elaborate on this subject in the next slide, but here I'm trying to give you the big picture of what that paper was talking about to lead to the Q filter. So the second part of this paper is actually trying to solve a very difficult problem, which is reading cursive handwriting. And this is for offline. The project was for the post office, trying to automate the mail sorting. So we scan a mail and we convert it to text. So I'm gonna use this to tell you what we mean by model. So we have an input, which is just a word, for this case, like silver. We do the pre-processing that I mentioned before. We remove the slant, for example, and we remove, if there is underline or so, we remove it. And this is segmentation free, so it's supposed to tell me where the characters are and read the word. The way hidden Markov model is built to deal with this problem is a very deep neural network, actually. For each character A up to Z, we have a model for lowercase and uppercase. And for each word in the dictionary, try to tell me, Jad, if you can hear me from time to time, because I cannot hear any.
نعم متابعين جدا شكرا جزيلا.
Okay, so what do you mean? What do we mean by model? It's a hidden Markov model that has states for each part of the input, and it has transition probabilities. And we just go left to right and we compute output like in feed-forward neural network, but it's probabilistic. So we build the word models from the character models, like the character for B, O, S, T, O, N are concatenated to generate a model for the word Boston. And then after we do the feature extraction, I'm going to skip that, but we get a sequence of vectors, high-dimensional vectors. And this is called continuous density hidden Markov model. It's a probabilistic statistical model that's being used for sequence analysis. So we match, we compute the probability of observing this sequence given each model. And after post-processing, it's going to give me a score for each of the hypotheses, the dictionary. Hopefully, in this case, the score for silver is the highest. Then we read it as silver. And you can see here examples, orange, grand, island. It's very difficult things even for humans to read sometimes. But that's the paper that's built using a generalized hidden Markov model. This is the data that they have to deal with from the post office. Look at the variation in just class uppercase A. This is an upper class A. This is an upper class A, believe it or not. This one, which looks like an F. So great variation of the inputs. That's why statistical models are used, because you cannot describe this by crisp rules. We have to deal with this statistically. So this is, you see in the right side hand side, this is the kind of noise that I need to remove, underlines, hanging bars from the upper bars and the lower bars sometimes, until I make it something like clean enough. And the opposite of the problems also exists. So the same button here for my phone number, the P, and the light, B, the H and the B, they are exactly the same. Is 5 and S are exactly the same. So if you insist on using probabilities, you are going either to read phone or number, because the score for H and B has to add to 1. And that makes probability, at least the additive probability, a little bit uh, difficult to be able to deal with this problem. That's what motivates using different kind of measures other than probability measures. So now we are going to talk about the analysis. In mathematical analysis, we have 3 elements. Call them measures, like probability measure, belief measure, plausibility measure. And we have metrics, like Euclidean metrics, Manhattan metrics, Max metrics. And the way we integrate, we aggregate the information, as I said before, the classical models use averaging, a weighted sum. That's also a problem, because we want to go above the average or below. The average is always between min and max of the inputs. So the classical models use probability, Euclidean distance, and average. And we want to expand. So let me first just try to expand and describe to you what we mean by Q measures. So the Q measures can include all of those as special cases based on a single parameter called lambda, right? First, let us just fix the Euclidean and the averaging aggregators, the Euclidean distance, and just try to find the formula, the mathematical program, if you like, all the algorithms to be able to cover this space about measures. I'm sorry, I have to go a little bit deeper mathematically, because everything here is math, by the way, and all computation intelligence is a strongly mathematical framework. We cannot just make ad hocs or something like that and claim that this should work. So I'm talking here about fuzzy, but it's general, it's measure theory. Probability measure is defined if A and B are non-intersecting sets. The empty sets measure is 0, the full set is 1, and when the set increases in size, the measure has to increase. Everything that satisfies those axioms is called a proper measure. So probability is just one special case where the probability of A union B is the probability of A plus the probability of B. Sugano is a Japanese scientist who is very known for doing fuzzy logic, came up with a measure called the lambda measure. And he said, I'm going to add one term, lambda times the product here. But the problem is there is only one lambda that can satisfy the measure of the full set the space equal to 1. That makes this measure a little bit restrictive. And I said in the Q measures, I don't want lambda to be unique. I want it to be variable, actually. And for each value of it, it can behave differently. And I proved that this equation here, I'm just writing it to define it, but this is not how we compute it because this could lead to some numerical problems because we are multiplying numbers between 0 and 1s probably, or large numbers it can overflow or underflow. But I'm going to talk about that later. Anyway, the parameters for this measure is, we call them Fi here, which are density generators. They are not the density yet. There are numbers from them we generate density. There is an IEEE transaction paper that describe these things. And there is a beautiful, actually, convergence theorem to say that this, if you repeat doing it by every time is scaling somehow, you're going to convert to Sogano measure where 1, the term that we divide with, it becomes 1. So it's converging. If you are dying to use Sogano measure, we give you a way to do it. But I'm interested in every steps before converging, and that's what gives me the huge capacity for the filter. So why is that important? It's very intriguing to think nonlinearly right now. If you are looking at a pixel on a 3x3 neighborhood, and we call those pixel values x1 up to x9. If I said set 1, set A is x2, x3, x4, and B, which is the complement of A, is the rest of the states or pixels, if you like, you find that's the relation between your certainty in A and your certainty in non-A is linear for probability measure, right? Because the probability of A is equal to 1 minus the probability of not A. But this is very restrictive. Now with the Q measure, I can go below this curve or above depending on the value of lambda. And more interestingly, if I said that's the probability of A is alpha divided by rho here. This is the ugly math. Sorry, I'm not going to go over the math, but I want to give you a feel about the capacity of this model. The model is saying, I don't know what's the probability of not A, because an infinite number of curves exist, and I don't know which one of them is not A. This makes you be able to characterize a lot of things, like you can say actually the probability or the certainty of an event A, an event is a set, is 90%, 0.9. And you can have the probability of not A also 0.9 or 0.95. That cannot be characterized by probability, by what we call it precise probabilities. There is something called non-precise probability that can capture it. I know we have statisticians here with us. And we can say, or even if I can say, for example, the probability is going to rain tomorrow is 0.1, but the probability is not the probability. So the certainty, the Q measure, is 0.1, but the certainty is not going to rain is also 0.1. All what's important when your certainty increase, your uncertainty should not increase. And that's a great power that's going to give us tools to capture uncertainties that's hard to be captured with precise probabilities. I'm going to show you use cases where I couldn't solve some of the problems with any existing classical model, but I was able to solve it with this flexibility. And this is proven to be a proper measure. I just want to give you a feel in this first session about that. This game is deeply mathematical because we are going to reason in high dimension space and we cannot even see the data. We can try to project it to lower dimensions like 3 or 2, but the original data is high dimensional, and unless we try to capture the ambiguities and the uncertainties, that's going to be always the case for all of the use cases we talk about. It's going to be difficult. So how are we going to combine those pieces? Even with the measure, let us call the measure G in this expression. What's happening is if you have a function, which is what's inside the window of the filter, if you like, we keep thresholding this function at every possible threshold. So at threshold alpha, we have this A sub alpha is this part and this part. We call it the alpha cut. So this is a crisp set. We pass it through the measure and we plot alpha, the threshold, versus the measure. The area under this curve is the Choquet integral. So if the signal is very high, this curve is going to go higher, it give me a higher value. If it's the value of the function is low, it's going to go low. But nonlinearity is the name of the game. If you want to force it to be linear, we don't need to change anything. Just use probability measure or use Q measure with lambda equals 0. If we don't know, then we learn it using machine learning. Okay, this is the hardware that's going to be built for just the node. I'm showing you, for example, a 5-tap filter, S1 up to Sn. This is just part of my signal. And for 2D, it could be n by n. But here, let's just show it for a one-dimensional signal. So at each threshold, I'm going to have a binary sequence of zeros and one. I pass it through the Q function, I get an evidence about how high the signal is. If the signal is very high, those numbers are going to be high. If it's not, they are going to be low. There are zeros between values between 0 and 1. We add them up, we get the expected value. So all the game is about expected values. And it's non-traditional way of designing filters of doing statistics as well. So the processor get the parameters f1 up to f5, it's a vector, and get lambda, and in real time, it just compute those and give me them. For special settings of f and lambda, I can make it a dilation filter, an erosion filter with the same hardware. And I don't have to worry even about the size of the filter. It's all taken care of. So here's an example of an operation of a 3-tap median filter to just compare, which is the red line, m of f of n. The Q filter here is the yellow one, and the input signal is the blue one, if you can see it. And those are the threshold. From 1, I'm just showing values between 1 and this is 32 level digital signal. So when I do the thresholding at all of those, as I said before, the set is just going to be the ones here. I pass it through the 3 taps, then I get numbers between 0 and 1. And you can see when the values is very high, it's going to be ones. When it's between 0 and 1, does mean there is ambiguity here. And if I wanted to make it more ambiguous, I can increase the size of the window. Instead of 3, make it 5. And this is the correction that we are going to do, and we add up to get the yellow things. For a special setting, all those floating numbers could be taken to the extreme, 0 or 1. Then we get dilation or erosion of the signal, or something in between. So the Q filter is actually a robust estimator. People in statistics use robust estimators like order filters. The median is a special case of those filters, which is robust estimator. If you pay attention to what alpha is doing, the threshold, to the input signal, it's actually sorting the data. Because at high value, we are going to see the highest value, H4. We lower alpha, we are going to get H4 and H3 here. And we lower until the 0, then we get all of them. So, and the output of this Q filter right now is this area, which is highlighted in blue here. And to compute it, we multiply the value of the signal by this weight, which is the difference between 2 measures value. But I said this is not linear. Somebody might say, okay, it's a weighted sum. It's true, it's weighted sum, but if the order of the information change, the weight change on the fly. If the order doesn't change, we continue with the same weight. This is really very powerful, and it ties robust estimators to the Q filter node, if you like, which we are going to use it inside the network to solve our end-to-end problem. So this is just the number crunching that's going to be happening. It's actually add, multiply, and divide. Okay. So if I have a 5-tab filter, depending on the order of the information I can have, this is a 5 hypercube folded in just 2D to see. For each ordering, I'm going to get a bus from this node to that node. In this case, I'm showing this is the bus. But if the information change, I could be picking a different bus. That's why this theory is called theory of capacity, because a 5-tab filter actually have a 2 to the power 5 set of filters, linear filters. That's why it has huge capacity compared to the dot product in the neural network. So I'm trying to get rid of the dot products by doing this trick in neural network, in hidden Markov models, in whatever classical technique is using measures or metrics or so. We're going to talk about that in the next slides, can be enhanced significantly. With me, I am in now slide 18 yet. See it? Hello?
نعم.
Okay. The difficult problem where we need machine learning is how we can get those parameters, F1 up to F5. So we need to use training data, which is labeled in this case. But I'm going to talk about unsupervised learning and those kind of things. Here, just to introduce to you the difficulty of the problem is, okay, this can be done, as I said before, just recursively computing using the lambda rule. F of xy equal x plus y plus lambda xy in this manner. If I can sort the data, then the computation is just 5 steps. We will get the output of the filter. And we try to optimize for a set of input data for training with those targets, a scaled and shifted value, because we wanted to allow some freedom about shifting the data and scaling it with alpha or shifting it with beta. So that's require machine learning, and it's a nonlinear optimization technique. You can use any toolbox to be able to get the golden value of those Fs from which we build our filter. Well, I think this just described the number crunching, which is the mathematical theory. I'm going to share with you some use cases. This is the CDMA data, code division multiplexing, CDMA. It's used in mobile communication systems. And the application is called actually cognitive radio, where we're trying to use machine intelligence to figure out how to build a cognitive radio. So I got the data from an RF team that was using an existing linear filter that has 63 coefficients. That means 63 tab. There is echo yet, or somebody is talking.
نعم في شخص خاشبه اسم نعمات وكده لكن يسميه النيم فويس. أرجو إنك to be on mute.
Okay.
Just a minute. Yeah. So please mute yourself.
Okay. So
Go ahead. Yes. Proceed.
You can just mute everybody. So this classical technique is working very good in terms of achieving, we call it equalization. I don't want to talk about that, but it's a linear filter and 63 tab is latency. For communication, we are dealing with real time. That's they give me the data and said, we want to try your filter to solve the latency problem. I'm trying to give you example of machine intelligence. It's not about chatting. We have real world problems that we want to solve with intelligent devices or machine intelligence, call it AI, CI, whatever you like. I don't care. I just want to solve the problem. So, and I was able actually to train a 7-tab Q filter to match the performance of this linear filter. So I used the output of the linear filter as a target value in my training. And I split the data into training and testing, and I was able to get a highly correlated output from 7-tab. That's mean my latency becomes 3 instead of 32. Okay? So that's solving, just so you want to solve the problem of latency here. And I'm going to show you how the 3-tab Q filter was able to match the 63 tab target filter, which is linear. It looks it's just doing the job. They couldn't believe it. They said to me, we tried to lower the bandwidth for the linear filter to less than 63, but the performance dropped. How are you going to generate knowledge from 7 tabs? I said, you couldn't extract the knowledge from the 60, the less than 63 because your model is linear. But they have a 2 to the power 7 set of linear filters to be able to solve your problem, which is latency in this case, or CDMA data. This is another communication challenge. It's the power amplifier is the heart of your phone. And believe it or not, the efficiency of your PA, probably the electric engineering guys know that's 30 something. So 2/3 of the bar is going to be heat. So we have a trick for enhanced digital GSM evolution signals in communications called outphasing. So the trick is we express the signal as in phase and quadrature bars. It's a complex number, I plus JQ, if you like. And so the trick is to decompose any vector into 2 vectors, S1, SE is going to be decomposed into S1 and S2, but S1 and S2 has fixed lengths. And because it has fixed lengths, when we push it to the PA, the power amplifier, we are not challenging it. It's not going to degrade performance because we are easing the task for it. Theoretically, we know how to do that to compute it. But the problem is physically, when we build the circuits for it, a slight misalignment between S1 and S2 can generate noise, and we violate the requirements of the bandwidth. So what they did is to put a filter after S1 and S2 here, so that because the filter is an estimator, if you like, so that after going to the filter, we can go to the cheap PAs and we get good results. We tried to solve this problem with linear filters, FIR filters, those kind of filters are just weighted sum, but fixed weights. So we couldn't solve it because of a problem that I'm going to show you next. But when we trained the Q filter to do the job, we were able to solve the problem. So this is just showing you how the Q filter versions actually went much lower in noise. Sorry for the technical part about signal processing and spectral contents. My background is communication, but that's why I try to use AI or machine intelligence in communication systems, not in chat or handwriting. I wanted to solve it for products. So the challenge is actually, this is called a constellation diagram. This is the input signal can just go through these values. If we do it ideally, the outphase signals before filtering has to look, the constellation diagram is a nice ring. But with the filters, probably it's going to be like a donut like that. For some specific values, we are going to meet the design specifications. But if it becomes extremely filled, here the donut is almost like a disk, that's not going to work. So we compute something called the crest factor to be able to make this assessment. So first of all, we tried an FIR filter, a rated sum. It looks like, yeah, we can get good crest factor for each of S1 and S2, but we have very bad spectral content. That means those bands are going to be overlapping and it's crosstalk and those kind of things. When we try to use the FIR filter, this is not the Q filter yet. The problem reverse. We get very good crest factor, very good spectral content, but bad crest factor, which is because those filters has to be designed when we add them, we get the original signal. That's why one becomes good, the other one becomes bad. So no matter what you do, you're always going to get this dilemma. So we said, let us just use a Q filter. And that's what happens. We were able to solve the problem. We get good crest factor, good spectral content for S1 and S2. That's inspired us to design actually something that we call the smart power amplifier. You see, I'm trying to give use cases which is not just chatting, chat GPT and those kind of things. Although I'm going to talk about those language models in the next session, but I wanted to give the feel that computation intelligence is not just about chatting and videos and generating synthesized videos or even music or so. It's about solving problems in different domains, communications or not. We have very difficult problems to solve so that we can build useful devices. And this is just, so we saw we can extend the concept about outphasing. Instead of 2 branches, we make it n branches. And that's what I call a smart power amplifier. In my LinkedIn, you will find presentation about that technique. But the smart power amplifier is just using this trick. With the Q filter. And now I have multiple very cheap PA, here in this case, 18. And it says, give me more simple power amplifiers, and I can give you higher efficiency. You give me an infinite number, theoretically, of cheap power amplifiers, I give you 100% efficiency. And that sounds to be to be very challenging, not just theoretically how we can get that, it's physically when we build it with that number of things. All I need to take care of is actually I decompose the signal SE into 18 and just do the outphasing for the last two components. You see it here. You have a video in my LinkedIn showing you what's happening when this signal change and why the efficiency here almost doubled from, I said 30 for the classical power amplifier things up to 60 here with 18. But when I go with higher numbers, I can make this more. And power amplifiers are very important because right now, when we use the cloud, we send the data with the RF, with the modem, and we receive it, and that's going to drag the battery down. So I had to come up with this solution because I need an end-to-end solution for telepresence. And it turns out that the battery is a very important part. And that's why you see right now people are using machine learning to design even batteries. Here I'm using it in this case to design a smart power amplifier or an intelligent power amplifier. Okay, this is just, we talked about the measure. How am I doing in terms of time, Jad? Hello?
اخذنا هسه زي قول اخذنا ساعه مما بدينا يعني، فما دام
Okay.
كده فما عارف، خليني لا داير استاذنك لو
نعم.
نستمع اي ملاحظات. اوكي، ولا انت في اي ثينك سلايد رقم
خليني اغطي
جو هيد
السلايدز بعدين، ممكن الملاحظات ممكن نرجع للسلايدز الخصوصا. Okay, now we want to talk about metrics because that's going to be used in what I call support vector machine. We have a demo about that. I'm going to show you how we can use a different metric using the same trick, which is the lambda rule. And we want to extend from Euclidean distance to the full spectrum of metrics. So it's the same trick. Metrics are distance function. We want to characterize the distance between 2 points in high dimensional space. When they are the same point, has to be 0. When it's 0, that means x is equal to y, and it's symmetric. And we have the idea that the distance between x and y is plus y and z has to be greater than the distance between x and z, the trapezoidal axiom. So everything that satisfies this is called the metric. What we use in general is called p metrics. On neural networks, the dot products is actually nothing but p equal 2. It's the Euclidean thing. But this function is very powerful for any value of p if we sum over I the absolute values between each direction raised to the power p, and then we take the p root, which is very expensive operation, by the way, to do. Besides, we don't know which p is the golden one. We just speak, we say it's infinity, or it's 1, or it's like p equal 1 is the taxi cab, we go along the sides. Euclidean is the shortest distance, p equal 2. And even for some of the statistical models, we use something called Mahalanobis distance, which require computing a covariance matrix. And we are talking about high dimensional data. And inverting that covariance matrix is very expensive. So I wanted to get something good and inexpensive, which is very greedy. So I was able to show that if I scaled my vectors between 0 and 1, it becomes like inside a hypercube, a unit hypercube. Then the same lambda rule can be used to compute a metric. And for each value of lambda, we get a different kind of metric. This is when we plot the distance between 2 points equal 1. And I have 2 dimensions. And you can see where they match with P metrics. And P metrics are computation intensive. Here I just add multiply. That's very attractive computationally. And if I don't know what's the golden metric, actually lambda is between -1 and 0. I can just go through that range and find the best one. That's easier for the machine to figure out instead of trying to search for infinite value of B. I'm searching for it's still infinite, but it's bounded. It's not unbounded. And that makes life much easier. I'm not going to talk about support vector machines in details, but here I'm just trying to show you what's the impact of just replacing the metric inside support vector machine, which is a neural network, if you like. Okay, one support vector machine is a neural network where the nodes are actually real data points. That's the difference between it and a neural network, the classical one. But setting the parameters, those are called the parameters for support vector machine can make the behavior change significantly. And here I'm just showing you a 3-class problem, talking about classification, where color is the class. And this is a novel geometric base. This is the conventional one. I have actually an applet that I can run it if we got time. But we just let us describe what's happening. And but there is parameters to be tuned to figure out or to cross-validate the choices, if you like. In regression, we have noise data. We want to fit it with the curve, and you can see that the conventional one fitting is not as good as this novel one. And we get a smaller number of support vectors. So it's cheaper and it's better. So I think I have, let me try to show you a demo of that. Can you see uh, demo? I'm just gonna listen with you to see how this support vector machine can do classification and regression better than the classical one. And by the way, support vector machine is invented by the godfather of machine learning, a Russian scientist called Vabnik. So let us see the demo.
على إذنك يا دكتور ميدان، احنا هسه رجعت للكيو متريك بيز اس في ام، وما سامعين صوتك هسه. آه، سامعني؟ اوكي، فجأت السكرين اللي بعديها. هلو دكتور مجدي، ما سامعينك، احنا انت يو ار ميوت اي ثينك. ما معلش يا شباب، هو انتوا سامعينه كده هسه حاليا ولا؟
لا، ما في صوت منه.
دكتور مجدي، احنا ما سامعين الصوت.
كده كيف؟
ايوه، من من الكيو ماتريكس ديك. اوكي، الماتريك، فوقفنا على ما اظن سلايد 32 بعد ما تعرضت
for vector machine.
الفيكتور ماشين. يس.
Okay, let me go back to the slide 32. Can you see it now?
نعم، دي اخر واحده كنا شايفينها، لكن داير
كده بيك.
خلينا، ايوه دي اخر واحده كنا شايفينها. فعايزك يعني اقدر اقترح لك ان احنا ممكن نكون لانه almost على ساعه وربع، فلو اختصرت شويه او عشان نفتح الفرصه
انا
للنقاش.
خلاص،
اوكي،
خلينا نكسب الزمن في السلايدز الباقيه دي، بمشي فيها سريع عشان ندي فرصه للاسئله.
جدا، ثانك يو.
طيب، now we go to the aggregation, to the Q aggregate. We want to go across this. So we want to go beyond averaging. Okay? We want to go union intersection. And it's the same equation, lambda rule. Now we define it differently so that we can replace the generalized means, which is this equation. There's axioms for what we call an aggregator. So everything here is defined mathematically and it satisfies all the axioms. So it's the same equation, the lambda rule, we just how we normalize it, we are able to get a coverage of the classical aggregation operators. So if you can see the aggregator operator now, not just replacing the generalized mean, which is between min and max, it actually can go below and above. And that makes it a universal aggregation operator. And all we need to know is just figure out the golden value for this lambda. Here we are talking about logic and reasoning. So this is a use case where I just use the aggregator operator and minus to be able to do supervised learning for EKG signals. And I was able to compute the heart rate with this network that I couldn't do with any classical network. And you can see the original signal for heart is high, low, high, low, high, low, and sometimes it reverses low, high. This network is able to reverse it to high, low, which is very interesting in getting accurate computation of heart rate. This is heart rate for firefighters while they are conducting their job in the field. This is not a clinical setting to compute the heart rate. From EKG, they have a special suit. We use EKG signals. Again, this is a case for medical applications where it's not just chatting, it's solving real world problems. Okay, there is something called the radial basis function. which just use a metric, the classical metric, Euclidean distance. And we said, okay, let us just use the Q metric and leave everything as before. And this is cheaper and it solves some computation problems for us. We made it weighted. The math is a little bit look ugly, but I wanted to show you that it's very straightforward recursion to compute everything. We introduce one more parameters, we call it veracity operator, to be able to solve some of the problems. For regression and classification, by the way, machine learning is regression, classification, density estimation. That's it. Every problem is either regression, classification, or density estimation. Okay. This is because I mentioned that we are talking about neural network, genetic computing, and logic. Differential evaluation is a genetic algorithms that we used it actually to be able to train our models. So in this case, I'm showing you a case for RF positioning with a classical neural network. This is for regression. You can see how the error went down for the Q-based. And classification for driver maneuver. We want to tell the driver of a car whether it's safe or not with classical neural network with a Q radial basis function. And you can see the confusion matrix is enhanced significantly compared to this one. This is the error that we have, the diagonal here. We reduce it to these values. So what I'm delving it right now is something called Q logic. I'm close to end the job. Okay, it's the hardware that's okay. Right now we are not just using fuzzy logic. We want it to reason with only two operators, aggregate, negate. In the classical models, we have and, or, and not gates. In this new logic, even in fuzzy logic, there is three: union, intersection, and negation. In this new logic, which we call Q logic, characterize or and everything, as I showed before, with this simple function, the lambda rule: x plus y plus lambda xy plus 1 plus 1 times lambda 1, 1. And the negation operator is, instead of for probability 1 minus x, now it's 1 minus x divided by 1 plus lambda xy. So this becomes a generic negation operator. This becomes a generic aggregator. And we can do much better with this kind of reasoning. So very quickly, let us look at the value of lambda. Even for a fixed value of lambda, the node can behave as union here, as averaging here. So the behavior of the node is function of the parameters and the data is changing on the fly. If we change lambda, it's just the range is going to be bigger for the average and so forth until we go close to zero, where everything becomes union. But look at the behavior changing where the data is changing, even for a fixed value of lambda. When we go positive values, the operation reverses. It becomes intersection, you see here. And then this is lambda equal 0.1. Lambda equal 1 is the intersection area becomes bigger. And still the behavior is function of lambda and the data values. Here I have X and Y. Just to give you a feel about how this gate can change the behavior of union, intersection, or averaging depending on the data. So it's adapting to the data on the fly without changing anything. Of course, the obligation is how to find the golden parameters lambda. So this is just my summary for today's talk, Jack. And I start with definitions. Believe it or not, probability theory took 400 years to be accepted as a mathematical theory when it was formulated using measure and integral theory. 400 years. So I'm building on top of that to be able to go from probability theory to Q-measure theory. For optimization, while we will start it with least square, least mean square, now we're talking robust estimation, as I talked about order statistics and those kind of filters. The applications are dynamic systems, and most of the theory about dynamic system is based on this equation. F of x equal x squared plus c for every value of c. That's how it initiates. We're talking about decision-making, classification, and whatever. I base my formulation, which is the new thing here, on this golden equation, which takes into account how two things interact, which behave like a blending between or and. F of xy, depending on lambda, is x plus y plus lambda xy. When we compute something like the variance, for example, we have a function x minus x naught squared. The expected value of that function statistically is the integration of the function with respect to a measure, and that measure is characterized by a metric. In this new game, I'm saying don't stick with the classical Lebesgue integration, the classical probability measure, and the classical p-metric. Explore all of them and find the golden values for lambda aggregation, lambda measure, lambda metrics. This defines the network because even x naught here is an expected value. This is the average. So to compute x naught itself is another expected value. So this is what I was talking about the whole slides. Just we are redefining the expected value. We make it more powerful, but the obligation is the optimization to find the parameters. I hope that I cover this. This is the tough part about my presentation, by the way, which is what's the math behind the algorithms we are using and why machine learning is helping in building the model and in solving the use cases with the enhanced solutions. In the next session, hopefully we are going to see more use cases and the impact of using those tricks, if you like. But I hope that I made it a little bit attractive to you to go and dig. Everything I mentioned here, it's publicly available. So you can go to my LinkedIn and find documents and presentations and videos about this story. Next time we are going just to consume it. use it for solving problems that's hard enough to be solved.
اوكي شكرا جزيلا دكتور
We
مجدي.
talk also about what's the future. I can take questions right now.
نعم كويس جدا. نحن اول حاجه باسم المجموعه هي المجموعه بتاعت جيوماتكس، وفي مجموعه ممكن يكون عندهم الانترست في الارتفيشال انتليجنس. انا انك انت بتحبذ استخدام ماشين ليرنينج بدلا عن الاي اي. وزي ما ذكرت قبل احنا قدمنا الدعوه لاساتذه بتاع في قسم الكهرباء وكذلك في الاحصاء statistics اوكي وفي تخصصات متباينه يعني. ومعانا ناس اشتغلوا في المواضيع دي في اللي هو في الماشين ليرنينج واللانجوج لارج لانجوج مودلز من الفيس ريكوجنيشن لغايه كلاسيفيكيشن لغايه يس. فده كله موجودين. فنفتح الفرصه للنقاش والملاحظات يعني.
لو مسجلين السلايدز نمبر يكون كويس عشان
نعم
السلايدز اللي بتخص السؤال.
امير لو عندك مداخله.
انا والله عندي مداخله وعندي سؤال بالنسبه طبعا بالنسبه لنا احنا في الجيوماتيك اللي هو ماركوف موديل ده مهم جدا، لكن احنا بنستخدم اللي هو جاوس ماركوف موديل بالنسبه للكونتينيوس داتا. بالنسبه للداتا هنا بتكون ديستريكت وكونتينيوس صح في الموديل بتاعت
the model I showed you. It's a continuous density hidden Markov model. Let me go back to the slide where I talked about that. For the handwriting recognition, you see this is right. It's a vector of numbers. So we have an n-dimensional continuous space.
Continuous, okay.
This is a continuous. We don't do discrete. We tried the discrete hidden Markov model. This is a good question, actually. So the discrete hidden Markov model, we do vector quantization. We cluster the data. We are going to talk about clustering next slide, but it's a good question. And we replace each vector with a symbol. It becomes just the code for that vector. But here I'm talking about vectors with values between 0 and 1, actually, in this case. It's a continuous density. We started with the probabilistic hidden Markov model, which is the classical one. And we tried to enhance it with this generalized model, which is using the new aggregation, which is what we call it, the Shoke integral. And that gave us a boost. And in the paper, we combine the classical and something we call the possibilistic hidden Markov model, and the combinations improve significantly. Meaning there are cases they make different mistakes. The classical and this model, they make different mistakes. That's why when we combine them with the technique called board the count, we get something like 5% improvement. So and all the chain here between classical and model is how we integrate the data and which measure. If you stick, even if you use the same code, just you fix lambda to be 0 for the Q measure, you are getting the classical one, probabilistic hidden Markov model. So I hope that's we
إذا answered ده شكرا جزيلا. it's very powerful لأن احنا بنستخدمه هنا
right.
في
So hidden
الكونسل.
Markov model is used. Right, right. So you assume
بنستخدم
that's
الداتا بنعتبرها النورمال ديستريبيوتد، بعدين في
right,
كامل فلتر في الاستيميشن.
right. The assumption about Gaussian in all those models means it's linear.
linear yeah.
So when we say a Gaussian Kalman filter, it's a Gaussian statistical model actually, but it's linear. When we go to particle filters, then it's not linear because it's not necessarily Gaussian. To tell you the truth, in my whole life, I haven't seen a distribution that's normal.
Yeah, just as the assumption that and sometimes it's wrong. Yeah, you're right.
It's a very dangerous assumption. And all what I was trying to show you when I showed the example for support vector machine, have you seen the distribution? Let us just go here. Those are the three classes. Which one is Gaussian? Although this is not real data, but I'm just showing it when the data is not Gaussian, is not normally distributed. The classical statistical techniques suffer a lot because the assumption is violated.
Violated صح. وبالنسبة
We are
للجنراليزيشن
not
نحن بنستخدم
assuming
تايلور سيريز.
we are not
is good
assuming
assumption.
anything about the distribution. And that's the power. But there is number crunching that need to be done differently to get the fruit out of this model, right?
Yes,
So
yes, yes.
nothing comes just by trying. So hidden Markov model is really, this is the topic of my dissertation. By the way, I generalized hidden Markov model, and it was surprising to tell somebody that you generalize hidden Markov model because it's already the classical one is general. When you try to say I generalize it, that's mean I am doing the estimation differently. I'm using right now robust estimator mechanisms. And that's very, very attractive. So I'm not just trying to sell different theory for the sake of difference. It's for the sake of getting more accurate results. So
جدا شكرا سمح. بالنسبة للشباب الموجودين والطلاب بتاعين الدراسات العليا، فلو في أي ملاحظات بالذات الناس اللي عندهم المتخصصين في المجالات بتاعت الكمبيوتر ساينس الارتفيشال انتليجنس وكده، لأن الدكتور مجدي تعرض للموضوع ده from mathematical gradations يعني واستيميشن، وتعرض بدل ان نستخدم مثلا اليوكليديان ديستانس البي از ايكوال تو 2 مشى ل يعني انواع مختلفه منهم يعني للبي. شايف برضو دكتور عباس موجود معانا والاخرين، فالفرصه معاكم يعني. علاء سامي، اتمنى انك انت دكتور كمال ولا ابنك علاء، فمرحب بكم يعني. والباشمهندسة سارة وكل الحضور يعني، الباشمهندس خالد.
أسأل أي سؤال يجي في ذهنكم. ما
أيوة.
الريسيرش ده كله جاي by questioning a definition بتاع ال expected value. We question probability theory. We question things that we have been using for centuries. So it's good to question even thing that we think that is already done.
جدا. اوكي تفضل دكتور عباس.
السلام عليكم وشكرا جزيلا للدعوة وشكرا للمحاضرة القيمة. يعني يمكن بصراحة ما فهمت ولا حاولت أن أفهم التكنيكال بارت يعني في الماشين ليرنينج although it is very relevant to our profession. سؤالي what is the role of the machine learning or AI if you like in rebuilding Sudan?
الرول بتاع right. الرول بتاع الماشين ليرنينج هو building the model. We keep talking about models, but how are we going to get their parameter values? If we have no clue about the physics of what things are happening, we just have data observations. Whether this data is labeled or unlabeled, machine learning helps in figuring out the golden values, which hard to do without it. So when you hear machine learning, just think about it as parameter estimation. That's what it is. It's all about estimation. When somebody gives you a neural networks with random weights, there's no knowledge. Unless you find the golden weights, which is machine learning, then it's not going to be useful. And the fact that right now AI or CI or whatever machine learning is becoming very, very active in research is because we have huge amount of data. And that's I was talking to Jad last time. That's happening because of the sensor technology. Most of the electronic devices we have right now, they are acquiring data. And because of the digital technology, we can store those data. Memory itself, because of digitizations, becomes huge. That's why those language models and whatever, they are using huge number of parameters. And there is no deterministic way of computing those parameters. So we have to use stochastic techniques. And in a nutshell, the problem of machine learning is always going to be nonlinear optimization. If you force linearity, you can get a closed form solution which is optimal with respect to what you assume the objective function, but it might not solve the problem. So sensors make data available. Digital technology make storing the data possible in clouds or even at the edge. And just averaging those models is right now how those huge applications are happening in the cloud, and they train in USA and in Europe and something like that. And all they do is they average the weights, believe it or not. Averaging the weights of those models help a lot, although we were questioning here the linear average, but that's what they do in right now. So parameter estimation. The key thing is what kind of estimators that give you a different kind of machine. You use a robust estimator, you get a robust machine. And by the way, in this game, if you talk to any statisticians, I hope we have some statistician in the audience. If you told somebody that my model is robust, he's going to ask you one question: where do you sort? If you tell him, oh, I'm not sorting, he tell you, don't call it robust. It's all about sorting. Those robust estimators, they make the optimization task difficult because it's non-linear, but they get you better results. So that's what machine learning is all about. Everything else is just buzzwords. Estimation, estimation, estimation.
اسمح لي يا دكتور مجدي، انا احاول اجاوب لدكتور عباس. الدكتور عباس العضو المؤسس ورئيس مجلس الاداره في يوكانا وكذا لفترات، وهو صاحب الفكره بتاعت يوكانا ورابطه خريج خرطوم بالولايات المتحده وكذا. كالاتي بس الدكتور عباس، انا بحاول في قبل يومين كنت بستمع ل خوان جنسن اللي بتاع انفيديا، كويس. فهو سئل سؤال قريب للسؤال اللي انت سالته، وهو على حسب الشغل بتاع الناس الارتفيشال انتليجنس مقسمين. هو بيتكلم عن 5 سميها سفيرز. في الاسفير الاول بدا خليه بيجي للاسفير الثاني الاول انرجي، كويس. انا عشان كده لانه ان ذا اند الماشين ليرنينج دي والكلاودز والكمبيوتر واللارج كمبيوتر بيحتاج لانرجي، فدي واحده من ضمن الارياز المفترض التكنولوجي والتقدم يتم فيها. يعني الاستراتيفيكيشن الثانيه هي الشيبنج، شيب CHIP. اوكي. فالاندستري بتاع الشيبنج ده، لانه ده اللي حصل فيه الغفزه. الجزء الثالث اللي هو فيه الموديلنج واسع. نحن الشغل اللي شغال فيه دكتور مجدي ده في الجزء الثالث بتاع الموديلنج يعني. وطبعا بعد ذاك ممكن تجي في الاكستراكشن اوف نوليدج اللي احنا في السفير الرابع يعني and so on. وممكن يكون دكتور مجدي اي ثينك انت عندك واحده من السلايدز انا ما عارفها، ممكن تتغطى المره الجايه وكده، اللي فيها من الداتا going up to الويزدم وكده.
في session 2 I'm going to talk about that.
وده في الجزء اللي بعد. يس
نعم. الديجيتال تكنولوجي خلى الاستورج ايزير لكن الثمن it takes a lot of power. Like right now في الموبايل بتاعك الGPU اللي هو بنستخدمه في النيورال نتوركس وفي هيدن ماركوف موديلز كده للديكودر at least it drags the battery down. So a challenge right now is if you do analog مثلا electrical بيعرفوا it's الباور consumptions بيكون less. لكن how are you going to share information? How are you going to store it? So it opens another dilemma. My expectation, I'm going to talk about that next time, is the future is going to be something hybrid between digital and analog. And we most of the time when we are facing these two alternatives, an agreement between them in the middle, hybrid. Even in machine learning, there's supervised, unsupervised, and reinforcement learning, which is hybrid. We always end up with something which is a blending between technologies. And when we design devices, we end up always with doing an engineering combination of technologies. But the question about why do we need machine learning? That's the core of the question. It's parameter estimation. If those neural networks can figure out their weights by themselves, we don't need machine learning. And that's why unsupervised learning is difficult. Because you just have the data, it might have clusters, but to find those clusters without supervision, it's an MB hard problem, as we say in computer science. So machine learning is about figuring out whether it's supervised, not supervised. We cannot have a closed form solution for each parameter. We say AIA is equal X plus Y plus, no, we cannot do that. We just have to show examples. And then machine learning is just an optimization. That's what it is. It's just optimization of the parameters.
في أي ملاحظات ثانية وكذا؟ شكرا دكتور مجدي. في أي ملاحظة ثانية أو سؤال؟
I'm sorry guys, الماتيريال دي I know هي غريبة حتى للناس اللي في مجال because Motorola was holding this information because of the patents for long time. And now I got an approval to be able to
معلش يا دكتور مجدي، يا عماد انت تفضل يا عماد عمر، لانك انت ممكن تفتح المايك، لانه احنا سامعين عماد عمر. تفضل يا عماد. اوكي واصل يا دكتور مجدي سمح.
اوكي. I think it's a very good question to say, what can we do with machine learning or machine intelligence, if you like, that we cannot do without? It's a very good question. And to tell you the truth, we just find that there is limitation of what we know, and to get around that limitations, we need more advanced tools. And the reason that we are talking about something you cannot see with your eye makes it harder. Imagine if you have a 360 by 360 image. Each pixel value is a dimension. That's the dimensionality. You cannot see it with your eyes. You need more advanced tools to do it. Before, when we do the classical computer vision, we used to reduce the dimensionality. We don't deal with the pixel value. We make it smaller, we make it subzones, so that we can get around this story. But as I told you, this is no longer the game right now, even for not just chatting, is for making a machine that's adapt to the input. It's very challenging. Just adaptive filters. Adapt to what? How do you know that? I'm going to talk about this in the next session. How do you know that's what you build is better? So how do we make the assessment? I'm going to talk about that, how we compute some statistical numbers, and we plot curves. I'm going to talk about that, how to make sure that we are solving the problem, not just making sure that this model is better than that model. Even if you are improving your machine, how do you know that it's improving? You have to have a way of figuring out how to make the assessment.
سارة عندك سؤال؟ شايف فتحت المايك إذا عندك أي سؤال.
تاكيدا لكلامك يا دكتور مجدي، انا اشتغلت مشروع بتاع الويت افريج ده لجي بي اس داتا مع
ايوه.
برسايز تايمينج اللي هو البي تي بي. ده بيستخدموه في الترانسفير تايم للنتورك، وليه اوربت داتا. فالويتد افريج طلع احسن من الكارمال فلتر واحسن من النيورال نتورك داتا لسمول سب اوف داتا.
It could. I'm not saying that it's bad. I'm saying that it's just one option.
Is one option, yeah, yeah. Like
And
for large
and,
data, yeah, you have to
and if
use,
you,
yeah,
and
the
if you
weighted
look
estimation.
right, if you look carefully, we put a lot of engineering to make the weighted sum work. That's by itself, the engineering makes it nonlinear because you constrain it. And I told you the case where if the signal is just going up and you use this nonlinear aggregator, the weights are going to be fixed because when you move your window across that increasing signal, the order of the inputs is not changing. So it's just changing the weight if it needs to be changed. So you want a machine that you want the machine to do that without you telling it to do it. So the weighted sum could be working for some range of the data. But look at something like a stock market, those jump. I wanted actually to show you the support vector machine when a big jump happened in the signal. What's going to happen if you just average? You're just going to smooth it to believe the outliers. You want a mechanism, the whole AI thing is how you can overlook some of the data and just focus on the part that's need to be used. And that cannot be done by averaging. If you look at the median, it's just selecting one value from n values. And it's robust. It's not the average. It's an averaging operator, but it's not a linear averaging operator. What we call robust estimators are all like that, not just the median. So, and this is where the human intelligence is very superior. You can overlook part of the data completely and get very good estimates by humans. So the mechanism that I showed you, the difference between two measures, which is the weight, would be zero. So effectively, you can ignore some of the data. Actually, the dilation and erosion filters are ignoring a lot of the data because they are min and max of the window values instead of the median. They are robust estimators. And you talk to anybody in computer vision, you tell him that can you deal with that with the data without doing any morphological filters, which is min and max. You say, oh, it's going to be very difficult. So averaging could work for a range. And sometimes we try to make it, the engineering is to make it piecewise linear. You see, from one region to another region, you have a different set of weights. So for that piece of the data, it's linear, but not all over the space, particularly when you are talking with dynamical systems. And heat change the behavior of those sensors. Electric engineers know that. Weather change, what you get from optical sensors for the images. I'm going to show you some video processing use cases in the second session. Just putting two cameras, shoulder to shoulder. Each camera sees the light differently and the colors differently. Imagine the impact of heat, the impact of outdoor. So we want to build models. Somebody was talking about GPS. Some of the work I did for landmine detection for the Army is actually the GPS is not assisted. Is the error could be plus or minus 5 meters. You want to average in that error margin, it's not gonna work. The average could work with assisted GPS. You are helping it. That's the engineering. You are linearizing the data before you use the model, which is weighted. And that's engineering. That's good engineering. I'm not saying don't do it. But the way it's done is very, very difficult. And solving one problem does not solve the rest of the world problems. We just move from the soil here in US to the soil in Afghanistan or so. It's a totally different story. Totally different. Everything is different. This is for landmine detection, which is a computer vision task. We just want to see what's buried under the ground. It could be wet, it could be dry, it could be, we use satellite data to see where there is green, there is no green to help. But you can't say, okay, we are done. Just use linear models. It's life is, we are facing more complex tasks. And now because data is available, it's crystal clear that there is big challenge about how to, it's not just intelligence, it has more important than intelligence is actually coherence. You want a solution that's, it's more important than intelligence is how we develop it and how we sustain, which is how to cope with the environment. That's we are trying to model.
شكرا جزيلا. رايك شنو يا باشمهندس امير؟ اختم
لا في واحد اسمه سهيل عنده سؤال يا استاذ محمد.
اوكي جو اهيد. الفرصه معك. لان انا ما ظهر لي انه في.
If there is question in the chat, you can just read it to me because I can't see it from my.
ما ظهر بالنسبه لي انا السؤال.
I'm looking at this.
اوكي. فانا حقوم ادايرك يا باشمهندس امير تختم، وبعد ذاك بنقفل التسجيل ونستمع بعد ذاك، يعني دي الفكره. فجو هيك باشمهندس امير اختم الجلسه، بعد ذاك ادي الفرصه للدكتور مجدي.
والله دكتور مجدي كلام مفيد جدا، وده قوه الماس زي ما انت قلت behind الماشين ليرنينج والارتفيشال انتليجنس وحتى البيزك ماس اللي هو الايرور استيميشن والستاتستيك موديلز behind الحياه دي. فمفيد جدا ان الناس تهتم بالبيزك ماس، حتى لو خاشين في الشات جي بي تي والحياه دي عشان يعرفوا الحياه behind دي كيف انهم هم عملوها. وحتى حتى في الكودينج حسي بقت انت ممكن تفشل الشات جي بي تي وكان كود اني بروجرام ايزيلي، لكن لو عرفت البيزك you will understand how this work.
Exactly.
فانا بديك البلاتفورم تختم.
I think most of the sciences right now are using some sort of machine intelligence inside them. It's not just about communication, electronics, and those kind of things. Even in something like poetry, I'm going to talk about some examples where you can generate those, what we call them generative. I'm going to talk about discriminative and generative. in the next session. But how you generate new music, new pictures, new videos, new medicine, you name it, everything. It's gonna be like a watch in your hand. It's a utility. You don't want to use it, somebody else is going to use it and get better results because it's very powerful and because we have huge number crunching facilities. We can search huge, look about those models that you are using right now in ChatGPT or whatever large language models. Billions of parameters. How do you expect to estimate billion of parameters with the old way? It's going to be just difficult or time consuming. Whatever you do right now in 1 month, probably you can do it in few seconds with those new tools. The data is there. And some people think that the machine cannot be smarter than humans. Well, I'll tell you, in high dimensional spaces, the machine can be better than a human. Believe it or not, because you can give the machine very high dimensional data, thousands of dimensions, without labeling it, telling it this is class 1, class 2, class 3, and it can cluster it for you. How are you going to cluster that kind of data by human? Even the size of your memory might not be able to hold that amount of data to figure out the best clusters. The machine can do some things better than humans. Human can do some other things better than machines. But every trick that human use and he knows about it, it can also be used by the machine. If you are able to just characterize your trick to the machine, you should be able to do it. And I'm not going to talk about consciousness and those kind of things. That's beyond. We have problems. We want solutions. I don't care even that I should follow our understanding of the biological neural system to solve problems. I am an engineer. The best airplane right now flies better than birds, than humans. And it doesn't fly like birds. Does it? Your car, does it move like horse? It doesn't. But it solved the problem. It moves faster than humans, than horses. That's what we are. That's how we look at it. So we are not just following our understanding of the biological neural network or what's. Although if we know, that's good. We'll use it. But we want to solve the problem. Probably was every time we try to solve problems as humans, we create other problems. But that's life. You have to solve whatever we can solve. With machine, without machine, that's the challenge. I think that's what I just wanted to lay the foundation today, to say this is mathematics. And a lot of sciences are becoming mathematical science, even political science. Now it's a mathematical science, by the way.
شكرا جزيلا. في زول عنده سؤال جو اهيد SOHAI ولا حاجه زي دي؟ اتفضل او اتفضلي. Please unmute.
Can you do it from your end?